Nobody had ever reached the deepest point of Lake Tahoe. Not a human diver, not a submarine, not a single piece of equipment in the entire recorded history of exploration at what is consistently rated one of the most beautiful lakes on the planet. Then, on September 5th, 2025, a custom-built robot descended nearly 1,600 feet through absolute darkness, touched the bottom, switched on its lights, and transmitted live footage to thousands of people watching online. What the cameras captured rewrote what scientists believed about this lake, confirmed things that had only been theorized, and revealed a hidden record stretching back 12,000 years that nobody expected to find in such extraordinary detail. This video covers everything the dive actually showed, what the science says about it, and the one finding that researchers described as genuinely unexpected given what they thought they already knew about this body of water. Lake Tahoe spans the border of California and Nevada in the Sierra Nevada mountain range at an elevation of 6,225 feet above sea level. It is 22 miles long, 12 miles wide at its broadest point, and covers roughly 191 square miles of surface area. The water is famously clear. Decades of research by the UC Davis Tahoe Environmental Research Center have measured exactly how far down light penetrates, and in its best recorded years, the answer has been around 75 feet of visible depth when measured by the Secchi disk method, a white disk lowered until it disappears from view. The clarity comes from a combination of factors. The elevation filters out pollutants that settle at lower altitudes, the watershed is largely granitic bedrock that releases minimal sediment, and the deep cold water stratifies in ways that reduce the biological material suspended in the upper layers. The lake holds a maximum depth of approximately 1,545 feet, making it the second deepest lake in the United States, after Crater Lake in Oregon. But while Crater Lake's bottom had been mapped and studied extensively, Lake Tahoe's deepest point had never been directly accessed by any instrument. The sediment layers resting there represented an undisturbed archive of everything that had happened in the region for thousands of years, and nobody had seen it. The ROV that changed that was called Deep Emerald, nicknamed Emmy, short for Deep Emerald. It was built at a cost of nearly $50,000, equipped with a custom 600-foot fiber optic tether for live high-definition video transmission, and purpose-built to withstand 50 atmospheres of pressure at depth. The pressure at 1,600 feet underwater is approximately 50 times greater than atmospheric pressure at sea level. That means every square inch of the ROV's housing was bearing roughly 750 pounds of force from the surrounding water column. The fiber optic tether allowed real-time 4K video to transmit continuously from the lake bed to the surface vessel without signal degradation across the full depth. The project was a partnership between the Restore the Lake Depths Foundation and the Tahoe Fund. Lindsay Koff, the founder of Restore the Lake Depths, piloted the ROV herself, having previously led operations to pull 80 tires from the lake floor. She described controlling the ROV as like playing her favorite video game, but with significantly higher stakes. 20 test runs were conducted before the main dive to verify the equipment, calibrate the cameras, and ensure the tether management system could handle the full depth without tangling or introducing a slack that would reduce control precision at the extreme end of the line. When Emmy's lights came on at the bottom, the first thing researchers noticed was not the spectacular geology or the biological activity that had been theorized about. It was the sediment. The lake bed at Lake Tahoe's deepest point is covered in an extraordinarily fine layer of material that has been accumulating continuously for thousands of years. It is not rough or rocky, it is smooth, it is soft. And it is, in its own way, one of the most information-rich surfaces on Earth for understanding the regional history of the past 12 millennia. The Tahoe Fund's post-dive briefing confirmed that sediment cores taken from the lake contain layer after layer of preserved geological and environmental data. One of the most significant is a layer of ash from the eruption of Mount Mazama approximately 8,000 years ago. Mount Mazama's eruption was the volcanic event that formed Crater Lake in Oregon, one of the largest volcanic events in North America in the past 10,000 years. That distinctive ash layer provides a precise reference point in the sediment column for dating everything above and below it. The cores also revealed evidence of a massive underwater landslide that occurred in the lake sometime before 12,000 years ago, preserved as a distinct disruption layer in the sediment record. Additionally, the cores show the extensive logging that occurred in the Comstock era during the 19th century as a surge of sedimentation that shows up clearly in the stratigraphy, and then the improvement in water quality and reduction in sedimentation following environmental regulations introduced in the 1970s. Or think about what that means as a scientific archive. 100 feet of sediment recording 12,000 years of continuous regional history, stored in an undisturbed cold, dark environment, with a precisely dated ash layer marking a specific moment in time that allows every layer above and below to be placed in a known chronological sequence. The sediment cores from Lake Tahoe's deepest point function as a regional climate record, a fire history record, a geological event record, and an anthropogenic impact record simultaneously. The dive made it possible to observe the surface of this archive in situ for the first time, and to collect samples from areas that surface-deployed coring equipment could never have targeted with the precision that a direct observation ROV provides. The lake's clarity at depth was one of the first things viewers watching the live stream commented on. In many deepwater systems, organic matter, suspended particles, and biological activity cloud the water column at intermediate depths before it clears again near the bottom. In Lake Tahoe, the water at the bottom remained extraordinarily transparent. Emmy's lights illuminated the lake bed several meters ahead, with minimal scatter from the water column itself. Sudeep Chandra, foundation professor of limnology at the University of Nevada, Reno, who participated in the expert panel during the live stream, explained that the clarity is maintained by the cold water stratification that prevents mixing of nutrient-rich bottom water with the clearer upper layers, combined with the granite geology of the watershed that contributes minimal dissolved minerals or particulate material to the lake system. The biological findings from the deep footage were among the most discussed in the immediate aftermath of the dive. Life at 1,600 feet in a high-altitude freshwater lake with near-freezing temperatures is not zero, but it is sparse and adapted to conditions that would be lethal to most organisms. What Emmy's cameras showed was a population of organisms living in the sediment surface layers, visible as subtle disturbances in the fine material and, in some cases, directly captured in footage. The organisms present at these extreme depths in Lake Tahoe are primarily invertebrates adapted to cold, dark, low-oxygen conditions. Their presence at the very deepest point confirms that even the most extreme zone of the lake supports a functioning, if minimal, ecosystem. The geological structures visible in the footage gave researchers their most direct look at the underwater topography of the deepest sections. Previous mapping of the lake floor had been conducted by acoustic methods, primarily multi-beam sonar surveys that build up a picture of the seafloor topography from reflected sound signals. But acoustic mapping cannot show surface texture, sediment composition, small-scale biological activity, or the visual character of the terrain in the way that direct camera footage does. What Emmy captured confirmed the existence of the steeply sloping walls that descend from the lake's shallower margins toward the deep basin, showing the dramatic vertical relief of the underwater landscape that makes the deepest point such a distinct and isolated environment from the rest of the lake system. The drought context that preceded and coincided with the dive significantly shaped the scientific moment it represented. Historic drought conditions between 2024 and 2025 pulled the lake's surface down by nearly 9 feet, exposing sections of the shoreline that had not been above water in living memory. As the water level dropped, divers and ROV operators who had been working in the shallower accessible zones began documenting things that had been submerged for decades. Among the findings along the exposed and newly accessible bottom edges were hundreds of corroded industrial barrels leaking heavy metals and abandoned vehicles that had been sitting on the lakebed for an extended period. The barrel discovery was the aspect of the drought-era findings that attracted the most attention because of its environmental implications. Corroded containers leaking heavy metals into a body of water that supplies drinking water to several communities, and that has been maintained for decades. As one of the clearest lakes in the world, represents a direct threat to the water quality that the region has invested heavily in protecting. Environmental monitoring expanded significantly in response to these findings, with researchers using both the period of lower water levels and the subsequent recovery to track whether any measurable contamination spread from the identified barrel locations into the broader water column. In early 2026, heavy winter storms drove a significant recovery in lake levels, with billions of gallons returning and once again covering sections of the newly exposed lakebed. The recovery is considered positive for the lake's overall water storage, but it also resubmerged some of the barrel locations that researchers had been actively monitoring, creating a need for continued ROV-based access to those specific sites to track contamination levels. The combination of the deep dive footage from Emmy and the ongoing environmental work around the barrel sites created a moment in 2025 and 2026 in which Lake Tahoe received more scientific attention from the underwater perspective than at any point since systematic research on the lake began. The two threads, the deep archive dive and the shallow contamination monitoring, are separate in their scientific focus, but connected in what they reveal about the lake as a system. The sediment record at the bottom shows the full arc of human impact on the watershed, from prehistoric events, through the logging era, through modern environmental degradation, and the partial recovery that followed regulation. The barrel sites and the materials found along the drought-exposed margins are the latest chapter in that ongoing human impact record, one that is still being written. The scientific infrastructure established around the Emmy dive is designed to be permanent and expanding. Looking ahead, those involved in the mission expressed the belief that Emmy's dive opens new possibilities for collaboration. saying that universities, research groups, and organizations that had not previously had the resources or equipment to explore the lake at this level can now work with the Foundation to access data that empowers education and research at depths previously beyond reach. The ROV is available for collaborative scientific deployments, and the footage and data from the initial dive have already been integrated into research programs studying the lake's geology, biology, and water quality dynamics. The UC Davis Tahoe Environmental Research Center released its 2025 Clarity Report in June 2026, continuing the nearly 60-year record of Secchi disk measurements that tracks the long-term trajectory of the lake's famous transparency. That dataset, stretching back to 1968, is one of the longest continuous limnological monitoring records in North America and shows both a deterioration in clarity that occurred through the mid-20th century and the partial recovery that followed the environmental regulations of the 1970s. The deep dive provides complementary data by allowing researchers to directly observe and sample the sediment layers that record that same history in the solid substrate rather than the water column. The myths that had grown up around Lake Tahoe's depths over the decades, fed by its inaccessibility and the cultural weight of being the largest freshwater lake in the Sierra Nevada, turned out to be more interesting than fiction in the places where they were replaced by direct observation, and more sobering in the places where what was found was not ancient mystery but modern waste. What the cameras actually recorded at the bottom was exactly what rigorous limnology, geology, and ecology predicted should be there, documented with a clarity and directness that only direct visual access makes possible. The preserved ash from a volcanic eruption 8,000 years away in both distance and time. The sediment disruption from an ancient underwater landslide. The biological community adapted to total darkness and near-freezing temperatures at the greatest depth of the second deepest lake in the United States. And the contamination legacy of a century of human activity in the watershed above. None of it required a monster or a crime boss. All of it was extraordinary. Subscribe and check back as the collaborative research program using EMI continues to generate new findings from Lake Tahoe's depths. The sediment archive down there has 12,000 years of regional history still being read, and each dive adds another page to what is being understood about a lake that has been sitting in the Sierra Nevada since the end of the last ice age, recording everything. The geology of Lake Tahoe itself explains why the deepest point is where it is, and why that location accumulated the sediment archive that the EMI dive revealed. The lake occupies a graben, a valley formed when a block of the Earth's crust dropped down along bounding fault lines on either side. The Sierra Nevada fault system on the west and the Carson Range faults on the east created the structural basin that the lake fills. The basin is not uniformly deep. It has a complex underwater topography with shallower sills, submerged ridges, forming distinct deep basins separated by underwater terrain that routing water and sediment towards specific low points. The deepest point, at approximately 1,545 feet, sits in the northern part of the lake. The topography slopes dramatically from the lake's edges toward that central deep, and the steep underwater walls that EMI's cameras captured during the descent are the expression of those ancient fault-controlled margins. The scale of those walls is something that acoustic mapping conveys in numbers, but that direct footage communicates in a completely different way. Swimming above what amounts to an underwater cliff that descends nearly 1,000 feet is not an experience that data tables prepare you for, and the researchers watching the live footage noted the visceral impact of seeing that terrain in real time. The lake formed its current configuration beginning roughly 2 million years ago, though the basin structure that contains it is considerably older. Volcanic activity in the region, associated with the broader volcanic field that produced peaks like Mount Lassen and the Cascade Chain to the north, contributed to damming the northern end of the basin and helping trap the water that filled the graben to create the lake. The lake has been at varying levels throughout its history, rising during wetter periods and dropping during droughts, and the sediment record at the bottom captures the record of those fluctuations in the particle size and composition of each successive layer. The Mount Mazama ash layer that the Tahoe Fund's experts highlighted during the EMI livestream deserves special attention because of what it represents in terms of precision geological dating. The Mazama eruption, approximately 8,000 years ago, produced a volume of ash distributed across an enormous geographic area of the Pacific Northwest and Intermountain West, where that ash settled into quiet water bodies and was preserved without subsequent disturbance. It created a precisely dated marker that geologists can identify chemically by the specific mineral composition of the volcanic glass shards. In Lake Tahoe's sediment column, the Mazama layer is clearly identifiable, and its presence creates a reference point that allows researchers to calculate deposition rates for the layers above and below it by measuring thickness and dividing by the time elapsed. The landslide deposit recorded in the sediment cores below the 12,000-year marker tells a different kind of geological story, A mass failure of underwater slope material, large enough to leave a distinctive disrupted horizon in the sediment column across the deep basin, indicates a significant seismic or gravitational event in the early post-glacial period. The Sierra Nevada was actively adjusting to the loss of glacial ice mass around that time, with the reduction in ice loading causing a rebounding of the crust called isostatic rebound, and potentially triggering fault movements along the basin-bounding fault structures. A landslide of the scale recorded in the sediment at that approximate period would be consistent with this kind of post-glacial seismic activity. The water quality trajectory recorded in the sediment above the natural geological layers is equally revealing, but for different reasons. The logging of the Lake Tahoe watershed during the Comstock era of the 1860s through the 1890s was extraordinarily intensive. The silver mining operations in the Virginia City area on the Nevada side of the Sierra Nevada consumed timber for shaft supports, heating fuel, and building construction at rates that stripped entire mountain slopes of forest cover. That stripping immediately increased erosion rates across the watershed, and the resulting surge of fine sediment particles flowing into the lake and runoff shows up in the sediment column as a distinctly different layer than anything that preceded it in the natural geological record. The recovery layer above it, corresponding to the period after environmental regulations began restricting development and pollution inputs starting in the 1970s, shows a measurable shift back toward finer, lighter particle deposition. It does not return to pre-logging conditions because the watershed has been permanently altered in its vegetation cover, its road network, and its hydrological routing. But it shows that the lake is capable of partial recovery when the input of damaging material is reduced, which is the scientific foundation for every conservation investment that has been made in the watershed over the past 5 decades. UC Davis has been measuring that recovery with the Secchi disk clarity method continuously since 1968, and the long-term data set shows both the deterioration and the partial recovery in quantitative terms. What the sediment core record from the deep basin adds to that surface observation is the physical archive of what drove the changes. The disk measurements record what the water looks like. The sediment tells you why. The contamination story from the drought-exposed shallower margins is a separate but related thread that the scientific community is actively tracking. The barrels found in the shallow zones during the low water period of 2024 and 2025 are presumably from industrial disposal practices of decades past, when lake disposal of unwanted materials was not subject to the environmental regulations that govern such things today. The specific materials leaking from the corroded containers need to be characterized, and their contribution to the lake chemistry needs to be assessed against baseline measurements of the lake's heavy metal content. Lake Tahoe has particularly low levels of dissolved minerals compared to most lakes, a consequence of its granitic watershed that weathers slowly and releases minimal chemical content into the water. That low baseline makes any introduced heavy metal contamination more detectable and more significant relative to background than it would be in a more chemically active lake system. Early indications from monitoring around the barrel sites were that contamination had not spread widely into the open water column, but the recovery of lake levels in early 2026 requires ongoing ROV-based monitoring to track whether changes occur as water circulation shifts with the higher water levels. The Restore the Lake Depths Foundation and the Tahoe Fund have positioned the MEROV as a platform not just for single dramatic firsts, but for the kind of systematic repeated access to specific sites that environmental monitoring requires. Comparing footage and sediment samples from the same locations across multiple years is how you detect change. The first deep dive to the bottom established the baseline. Every subsequent dive adds a data point on whether conditions at the deepest point are stable, improving, or degrading. This matters particularly because the deep, cold bottom water of Lake Tahoe is one of the mechanisms that has historically helped maintain its extraordinary clarity. If the bottom zone were ever to experience significant increases in biological productivity, driven by nutrient enrichment from the watershed, the resulting decomposition of that organic material could consume oxygen from the deep water, altering the stratification dynamics that keep the lake's upper layers clear. Monitoring the deep biology and chemistry directly is more informative than inferring conditions from surface or intermediate depth measurements alone. The public engagement dimension of the September 2025 dive was itself significant for the lake's conservation future. Thousands of people watched the live stream in real time, experiencing the descent through the water column and the first ever footage of the lake bed in a way that surface observation of the lake never allows. The educational impact of showing people what exists below the surface they know from swimming and boating, and connecting that hidden world to the conservation questions being debated in regulatory and planning contexts around the basin, creates a constituency for protection that abstract data never builds as effectively. Lindsay Koff's description of controlling the ROV as her favorite video game but with higher stakes captures something real about what the technology has done for conservation engagement at Lake Tahoe. The technical barrier that kept the deep lake inaccessible for the entire period of the lake's documented history has been lowered to the point where a conservation foundation can deploy a custom ROV to the deepest point and live stream the results. That accessibility changes not just what scientists can see, but who can participate in seeing it and who feels personally connected to what happens there. The myths gave way to the actual record. The mob victims were not there. Tahoe Tessie, the legendary lake monster borrowed from the cultural template of similar stories from Scotland and other deep, clear lakes, did not appear on Emmy's cameras. What was there was a 12,000-year sediment archive, a population of invertebrates adapted to cold darkness, a volcanic ash layer from an eruption 8,000 miles away in both time and distance, the geological scars of ancient landslides and fault movements, and a clear chemical record of everything humans have done to the watershed above. The lake has been recording everything that happened around it for longer than any written human record exists. Emmy gave us our first direct look at that archive, and at the world that has been sitting undisturbed at its deepest point since before the pyramids were built. Subscribe before you leave, because the research program at Lake Tahoe is ongoing, and every subsequent dive adds to a picture that is already more complete and more interesting than anyone imagined before the cameras went down. The September 5th, 2025 dive was the first time any machine reached the deepest point of Lake Tahoe, and everything Emmy's cameras recorded was real, documented, and scientifically significant. It was also, in every honest sense, just the beginning. The sediment archive at 1,600 feet records more than 12,000 years of continuous regional history, and the research teams now have the equipment and the institutional partnerships to keep reading it. The lake that hid its depths from every generation before ours finally showed its deepest face. What was found there was not a mystery. It was a record. And it is a record that scientists are only just beginning to read properly for the first time. Each one adds to it.